The James Webb Space Telescope, JWST, reveals the universe in extraordinary ways, showing us truly amazing phenomena and greatly improving our understanding of space. JWST just made a truly shocking discovery, identifying 700 galaxies trapped in black holes, including the Stepan Quintet, a group of 5 interacting galaxies. This announcement challenges our understanding of the universe. JWST is equipped with several state-of-the-art scientific instruments designed to observe the universe in an extraordinary range of frequencies. With a primary mirror more than 6.5 meters in diameter, this telescope surpasses its predecessor, the Hubble Space Telescope, in size, allowing it to collect and focus light from celestial objects with unparalleled precision and sensitivity. Its instruments include a powerful near-infrared camera, a mid-infrared spectrograph, and a stepless spectrograph, which together take images, measure spectra, and study the properties of objects from the oldest galaxies to the planets of our solar system. One of the wonders of the universe are black holes, massive entities that form as a result of the gravitational collapse of massive stars. When a star runs out of nuclear fuel, it experiences a supernova, which ejects the outer layers into space, leaving behind a dense core. When the mass of its core exceeds a critical limit, about 3 times the mass of our Sun, the gravitational forces become strong enough to cause a major collapse, resulting in a singularity at the center, a point of infinite density and gravity. Although the singularity cannot be directly observed, JWST has the ability to see further than any previous technology has achieved. One of the most amazing discoveries of JWST is the presence of 700 galaxies inside a black hole, challenging traditional understandings of black hole mechanics. The most important feature of a black hole is its event horizon, an invisible boundary beyond which even light cannot penetrate. This limit marks the point where the gravitational force becomes so strong that even photons cannot escape. Any object or radiation that crosses this boundary is inevitably drawn towards the nuclear singularity. A peculiar property known as time dilation occurs near the event horizon. As objects approach the event horizon, time appears to slow down relative to distant observers, a phenomenon predicted by Einstein's theory of relativity when space-time is warped by the enormous mass of a black hole. The event horizon is not a solid physical surface, but a mathematical boundary that makes direct observation difficult. However, their effect on the surrounding space can be observed. For example, with the help of gravitational lenses, the distortion of light caused by the enormous gravity of a black hole. Gravitational lensing, predicted by Einstein's theory of general relativity, occurs when massive objects such as black holes distort the surrounding space by bending light from nearby distant objects. This leads to visual distortions or enhancement of the image of the object. In the case of black holes, this effect is particularly strong and sometimes produces multiple images or entire rings of light, known as Einstein rings. Gravitational lensing has become an important tool for astronomers to study not only black holes, but also other massive celestial bodies. It is used to map the distribution of dark matter in the universe. Dark matter, which neither emits nor absorbs light, cannot be directly observed, but its existence is inferred from the effect of gravitational lensing. By analyzing the distorted light from distant galaxies, astronomers create detailed maps of dark matter that provide insights into the structure and evolution of the universe. One famous example of gravitational lensing is the Einstein cross, where a single quasar appears as 4 separate images surrounding the foreground galaxy. These observations confirm the predictions of general relativity and provide valuable information about the mass distribution in the lenticular galaxy. In addition to mapping dark matter, gravitational lensing has also been used to find exoplanets. When a star passes another from our perspective, the foreground star can act as a lens and amplify the light of the background star. When a planet orbits a foreground star, it can cause a temporary jolt called a microlensing event and help detect distant or faint exoplanets. Gravitational lensing also plays a crucial role in studying the expansion of the universe. Astronomers can measure the expansion rate of the universe by studying the light from distant supernovae and galaxies lensed by massive objects in between. Gravitational lenses are not limited to visible light. it extends to other parts of the electromagnetic spectrum, like radio waves and X-rays. Radio telescopes detect gravitational lensing from distant radio sources, and X-ray observations of galaxy clusters reveal lensing effects that map the distribution of hot gas and dark matter in those clusters. These multi-frequency observations provide a complete picture of the universe. Advanced telescopes like JWST, with their infrared capabilities, are poised to improve our understanding of gravitational lensing, allowing astronomers to study more distant and fainter objects. Shedding light on the early universe and the formation of the first galaxies, JWST's contribution to the study of gravitational lensing is expected to provide unprecedented insights into dark matter, the distribution of mass in the universe, and fundamental physics. Gravitational lensing is a powerful tool that is changing our understanding of the universe, allowing us to study the effects of massive objects on light from distant sources and providing valuable information about the mass, composition, and distribution of these objects. From mapping dark matter to finding exoplanets and measuring the expansion of the universe, gravitational lensing continues to be at the forefront of astronomical research. With advances in telescopes and technology, the study of gravitational lensing promises to reveal even more mysteries of the universe. Have you heard of white holes? The term comes from the mathematical solutions of the field equations of Einstein's theory of general relativity. These solutions refer to regions of spacetime where matter and energy are created, similar to how they are drawn into black holes. White holes only allow matter and energy to flow out. Nothing can pass from the outside to the inside, which distinguishes them from black holes. Some scientists speculate that white holes may connect to black holes through wormholes, suggesting that matter falling into a black hole may exit the white hole in another region of spacetime or another universe, which could explain the 700 galaxies identified in black galaxies. This idea is related to the concept of the multiverse, the hypothesis of multiple universes with different physical laws. Speculations that black holes could act as cosmic gateways or connections between multiverses or different regions of other universes are based on their ability to significantly distort spacetime. The study of black holes and their effects remains at the forefront of astrophysical research. Supermassive black holes, believed to be at the centers of most galaxies, can have profound effects on their environment. Their strong gravitational forces can disrupt nearby stars and gas clouds, producing powerful jets of particles known as active galactic nucleus (AGN) activity, which affects the rate of star formation and the evolution of galaxies. JWST is poised to significantly advance the understanding of AGN by observing these phenomena in extraordinary detail at different frequencies. Interstellar black holes, formed from the remnants of massive stars and supernova explosions, provide insight into stellar evolution and eventual gravitational collapse. Techniques such as X-ray astronomy and gravitational wave detection allow astronomers to identify and study these elusive objects in more detail.
Recent observations of gravitational waves from merging black hole binaries with instruments such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo have opened a new era in astronomy, allowing violent mergers to be directly observed and theoretical predictions to be confirmed. Future observatories such as the Laser Interferometer Space Antenna, LISA, will expand our ability to detect gravitational waves at greater distances and with greater sensitivity, providing an independent picture of the gravitational landscape of the universe. In addition to the study of black holes themselves, their gravitational influence extends to the behavior of stars and galaxies. Interactions between stars and black holes can cause tidal disturbances, where a star passing too close to a black hole is torn apart, creating bright bursts of radiation that can be seen from great distances. The study of black holes intersects with fundamental questions in physics, including the nature of spacetime and possible connections between quantum mechanics and gravity. Black holes are unique laboratories where the limits of our understanding are tested, especially in extreme gravitational fields where classical and quantum effects converge. One such theoretical concept is Hawking radiation, proposed by physicist Stephen Hawking, who proposes that pairs of virtual particles near the event horizon of a black hole produce thermal radiation emitted by the black hole. Although this has not yet been observed, its theoretical implications encourage ongoing research into the quantum properties of black holes. Understanding the formation and evolution of black holes provides clues about the early universe and the processes shaping its evolution. Massive black holes are believed to have played a crucial role in the evolution of galaxies and in controlling star formation. Black holes continue to fascinate scientists and the public. Black holes are one of the most exciting and challenging frontiers of astronomical research, from their role in galactic evolution to their connections to fundamental physics and cosmology. As observational techniques and theoretical models advance, our understanding of these complex objects will grow significantly in the coming decades, leading to new discoveries about the nature of space and the universe.